Okay, so the basic idea is I want to start with maybe a kind of motivating example, which is a classical result of Bonnison related to the isoparametric inequality, the standard one in the plane, and then remind everyone of the Minicozzi entropy from an hour ago, in case you forgot, and then maybe discuss the results we obtained. Okay, so let's get started. So right, so the basic kind of motivating problem for me is this classical isoparametric inequality. Sorry, it's going to move something out of the way. Right, so that says that basically if you start with a kind of reasonable domain in the plane, then of course you can control the area of the plane of the region by the length of its boundary. And of course you have equality. This is a sharp inequality with the constants here, and you get equality exactly on a disk, right? So right, so you basically I mean, this goes back, I guess, to the Aeneid, at least, sometimes called Queen Dido's problem. And of course, this gets generalized in higher dimensions, where you replace the area with the sort of n+1 dimensional volume of the ball, and the length of the boundary with the sort of surface measure. So here, this is my terminology using Hausdorff measure, and then there's some dimensional factors and a constant. And again, you have a sharp inequality that's achieved on only on balls. Right, and so then I think there was a talk yesterday, again, discussing this idea of if you have a sharp inequality, it's natural to study to the extent to which it's stable, and so there's many ways to do that, but in the context of the isoparametric inequality in the plane, one very interesting result is due to Bonnison, though, and essentially it says that right, if you have a domain, say omega, like so, not necessarily convex in this formulation, and you want to look at the extent to which the isoparametric inequality fails to be sharp. So that would be the difference between the square of the length and the suitable constant times the area. You can turn out to get a very sharp result that controls that in terms of the sort of in radius and the circumradius. So this would be, I mean, I'm not going to draw this perfectly, but essentially the the radius, say, of the largest disk contained in the region. So that's R in, and then you have the R out. Not a great artist. Apologize. So this would be the largest disk containing the smallest disk, sorry, containing the region, and right. And so what's interesting about this, of course, is that if you like, I mean, as the isoparametric defect gets very small, the difference in the two radii get very close to each other, and since they're in a sense nested, you're really saying that the set omega is close to the optimal set, which is the disk, in not just as not in a measured theoretic sense, but really in a very strong set. So as a set, right? So they're really quite close to each other as sets. So for instance, something very close to a disk, but with a small little nose coming out, right? Not hard to see that the length is much, you gain a lot of length with this poking thing coming out, but not much area. And so that has a large isobarometric defect, even though it's sort of close to the disk in a sense of measures. It's far as a set. So there's many related results, and Osserman has a nice sort of survey article on it, which he terms these sorts of results of Bonnison style inequalities. Okay, so there's of course a question of what happens in the higher dimensions, and it's not hard to see that this direct analog doesn't hold, right? So the idea is now if you try and draw this spike, right, now it sort of has some width, right? So this is not, this is again close to the ball in measure, but not close as a set. But the point is, this is has very small isoperimetric defect because the spike here contributes both very little to the area and to the volume. And of course, there are other notions of stability. So there's work of Fukuede, Hall, and Fusco, Maggi, Fratelli, but I'm kind of interested in this notion of stability as a set. So rather than look at this sort of isoperimetric problem, we're going to turn to a different problem, which is this Minicozzi entropy, which we saw previously. So let me just remind you what that is. And I take a slightly different perspective, even though it's equivalent. So again, it's coming ultimately from Euclid's monotonicity formula for the mean curvature flow, which Lu discussed. But the idea is basically you start with, say, a hypersurface in Euclidean space, and then you look at its Gaussian surface area, which is just the weighted volume surface area of the hypersurface where you weight by the Gaussian. And the point is this is a nice functional, but it's not invariant under the symmetries of Euclidean space. And so you kind of symmetrize it, if you like, by looking at the Gaussian surface area of all the dilation. So here this means dilate the surface by a factor rho, and translation. So here you move it around by this parameter y, and you take this supremum and you call this the entropy, or the Minicozzi entropy of the hypersurface, right? And if you go back to Lu's talk, she was changing the measure here to be different symmetries of the heat kernel. I'd like to change this hypersurface, but it's just a change of variable formula between the two. And it's worth mentioning that, and we'll see this has a large group of symmetries now, as we saw, and turns out this functional is kind of analogous in many ways to the Wilmore energy, which is something you can kind of exploit, and some people have. Okay, so what are the basic properties? Again, this is sort of just a recap of some of the things Lu said. So first of all, of course, by definition, the entropy is now invariant under all rigid motions of space, and also all dilations, and translations and scaling is obvious. Rotations is also not too hard to see because the measure is rotationally invariant. We also, as mentioned before, have that the entropy is at least one. And again, you have equality on a hyperplane. That's just a straightforward computation. And then finally, we have this very interesting monotonicity property, which essentially reduces to a computation done by Stone, which says that the entropies of the round spheres have a very nice monotone decreasing property as one increases the dimension. So they start a little bit above 3/2 when you're in dimension 2 in a circle, and then they keep decreasing as you go up in dimension, and eventually limiting to the square root of 2. And another thing that is worth mentioning, again, is obvious from the definition, is that just by Fubini's theorem, if you kind of take a cylinder over hypersurface, right, so I denote this as follows, right, so for example, if you took this, for me, S1 cross R1 is just the usual kind of round cylinder in R3, then the entropy doesn't change because the Gaussian area also will not change once when one does the integration out. Okay, so that's the basic properties. So then there's some not so basic properties, which of course are tied into the relationship of the quantity to the mean curvature flow. And so that says, first of all, as Lu mentioned, it's not increasing when you run the mean curvature flow. So along a mean curvature flow, the entropy is always not going up. It can stay constant even if you're not self-similars, but it's definitely not going up. Another thing is that there's this special class of hypersurfaces that are called self-shrinkers, And these are hypersurfaces satisfied that their mean curvature is proportional. This is the mean curvature vector is proportional to the normal component of the position vector with this factor minus a half. And they're important, again, because they're solutions to mean curvature flow that move purely by scaling down. And for these guys, you have that the entropy is actually achieved by the Gaussian surface area at the origin without dilating or translating. So this is, again, something Lu mentioned. And another sort of observation is that when sigma is closed, so it's a compact and without boundary, then in fact the entropy is strictly bigger than 1. And in fact, there's a dimensional constant strictly bigger than 1, so that the entropy is bounded from below by this dimensional constant. And so again, the question is to ask, what is the sharp choice of constant here? And again, we're calling this entropy. It's maybe supposed to be measuring complexity, and what's sort of the least complex closed surface, it would be the most symmetric one, which is the round sphere. And so it becomes natural to conjecture that it's achieved on round spheres. And I've, again, this is something Lu mentioned, but I'll reiterate it. So my student, Leitian Chen, kind of did this in the non-closed case where, we can see that not only is what's the simplest non-compact surface, it should be the plane, and the plane has entropy 1, and in fact, that's the only hypersurface with that entropy. Okay, so starting with this observation, of course, it led Kolding, Illman, and Minicozzi and White to conjecture that the only closed hypersurfaces with entropy that they have a uniform lower bound on the entropy that's sharp, and it's achieved on the round sphere. So if you're a closed hypersurface in Euclidean space, the entropy is bounded below by the round sphere. And again, you have equality if and only if you're a round sphere that's dilated or translated away from the unit 1. And again, this is the starting point of Lu's talk as well. And again, as she observed, right, the properties of the mean curvature flow. So for example, the curve shortening flow immediately imply this when n is equal to 2. Analogous results also imply it when n is convex or mean convex. So basically, in these cases, there's work of Huisken to essentially say that we understand where the flow is going and what it ends at, and we're able to recover the information about the initial hypersurface based on the singularity model. So again, a partial result was given by Kolding, Illman, and Minicozzi, who showed it for self-shrinkers, which again gave more credence to the conjecture. So when they're a closed self-shrinker, you have this entropy bound. And then Lu Wang and myself, as she mentioned, showed it in all dimensions. We showed it in full generality in this range of dimensions where the stability theory of minimal surfaces is the most well-behaved. And Jonathan Zhu extended it to all dimensions. And again, one might imagine the Kolding, Illman, and Minicozzi results kind of implied our results, but it's a little more complicated because there may be singularities sort of in between. There may not be a closed singularity at first. Like you might hit a non-closed singularity, in which case their result is not helpful, and it's a bit more subtle than just applying their result. Okay, so starting with this background, we can now move to the actual question, which is how can we understand the notion of stability for this inequality, and maybe in a different way than we saw before, which was a topological stability. So here we want to emphasize a kind of Bonasin-like stability result that we were able to prove. So this was something we did a little bit after we got the stability result. And so we showed that the following. So given an epsilon positive, there exists a delta greater than 0, so that if sigma is a closed surface and the entropy is just a little bit above that of the sphere, so this is a little bit above the sphere, then the in radius and out radius from before, well, it's always bounded from below by 1, but it's also bounded from above, in this case, by 1 plus epsilon, right? So in other words, if you take a surface and you draw this very thin spike, right, then the entropy here cannot be close to that of the sphere, even though if you look at the, say, Gaussian surface area of this guy, it's very close to that of S2. So the entropy is definitely detecting this spike in some way. So it's worth mentioning that the topological stability would say that that Lu had proved would show that if you had a little handle here, then the entropy is definitely away from that of S2. That's what the topological stability says. But here we even get it without a topological result. We even get it if there's just a spike here. And again, I should say I'm stating this to kind of be in accordance with what I described earlier. But when we actually proved it, we had a slightly more different terminology where we used a kind of Hausdorff distance of an appropriate store to the sphere. So what is the idea of the proof? Well, again, the idea of the proof is that the entropy is unlike the isoparametric inequality, is looking at all scales. So when we have a spike like this, right, this guy might have Gaussian surface area close to S2, but if you take this spike and you kind of zoom in on it, right, it kind of looks like a cylinder. And the cylinder, right, one can go back to this result of stone, and that we know that has a definite entropy away from that of the sphere, right? So that's kind of the heuristic idea. To actually make this precise, we use the mean curvature flow, and essentially the idea is that we actually proved a complete classification of the self-shrinkers in R3 of low entropy, and they basically have to be the shrinking sphere, a shrinking cylinder, or a static plane. And so we know the entropy here, this is not a singularity model. The entropy here is strictly less than the entropy here. So we have this result. And so when we're very close to the entropy of S2, we never see a cylindrical singularity. And so in fact, our flow exists all the way down to the time the flow disappears in a round point. And so there's a significant amount of regularity here. And essentially, by some kind of careful analysis, you can kind of argue that the tip here has to move very fast, and that's related to having something almost like a cylindrical singularity. And so when you're in this entropy very close to S2, not only are you a smooth flow, but you're actually a smooth flow with good kind of estimates on the speed the flow is moving. So this is a way of kind of controlling how the radius, the in and out radius, can change. And again, going back to this result, notice this is a ratio here because everything has to be invariant under dilation, because the entropy is dilation invariant. Okay, so we also showed, using slightly more careful analysis, a kind of quantitative version that was very similar in spirit to the Bernstein inequality. So basically, we showed that if you're closed, then you can always find a closed surface. You can always find a round sphere with some radius and some center, so that this sort of Hausdorff distance, where there's a scale invariant here, we're measuring with respect to the scale, is sort of a certain exponent of the difference between the entropy of the surface and the entropy of the two sphere, with some exponent 1/8. And I should remark, of course, it'd be nice to know what the sharp exponent is here, and the 1/8 is just for the proof, and we don't think it's sharp. But again, this is sort of saying that there's a really quantifiable way of how close you are to, in this Hausdorff sense, or as a set, in terms of the closeness of the entropies. Okay, so it's worth asking what happens in higher dimensions, right? So the proof that Lu and I gave really used the fact that in R3 we have a complete classification of self-shrinkers, right? That classification I mentioned. And such a classification is not known in higher dimensions. There's just not much that is known in that direction. However, there is a few things you can say, and using those things that you can say, my former PhD student, Lu Wang, was able to sort of show an analogous version of our stability result that held in every dimension. So again, when your entropy is sufficiently close to that of the round sphere, then your in and out radius have to be roughly the same size. So just a little bit less than as small as you like. And again, this avoids using the classification result because it doesn't exist, and is a much more involved argument using weak mean curvature flows and kind of methods of geometric measure theory. Okay, so maybe since I have maybe a few more minutes, let me just remark on one final result that I think is sort of interesting and has not really been published, but I think it's follows from our work, and I just thought I'd mention the conference. So there's a sort of related result that is about how close a surface is, how thin a surface can be when the entropy is not too big, basically. So it's not about the entropy being very, very close to that of the sphere where the Bonnison type result holds, but rather about saying that a notion of thinness for the set. So basically, if the entropy is not too far off from that of the cylinder, so you're a little bit below the cylinder, and this is sharp. If you're at the cylinder or a little above the cylinder, this type of result definitely can't hold. So if we define the thinness of a set, so let's say I have a set like this to be kind of the thinnest slab that contains the set, right? So this would be maybe the thinnest slab. So this might be right. So we know that the thinness is less than the radius of the biggest ball that contains it, and there's maybe a factor of 2 here. But of course, you could have a very, very flat set, and then this ratio would get very big. But what we can show, or what it follows from what we show, our argument is actually the entropy is small in this sense, then this ratio is actually not too big. So there's this bound, and of course the bound deteriorates as at least should deteriorate as epsilon goes to 0. So basically you can't be too thin and very, very big diameter, right? And again, everything has to be scale invariant. So that's why we look at this ratio. And again, this definitely is not something that is true for arbitrary hypersurfaces, because of course you can take a very long cylinder and then cap it off, and the entropy of that should be probably very close to that of the cylinder, maybe a little bit above. And definitely you can put that, you can make the outer radius as big as you like and make the thinness be, say, uniform. So this ratio can blow up. So again, this is the proof we give in our original paper, which is how we would prove this result from the previous slide, does not generalize easily to higher dimensions because it does not have this classification result. And even the argument that my student gave, Sheng Wen, it sort of only works when you're very close to the entropy of the round sphere. However, in his work, he kind of explains where the closeness is used, and it turns out that kind of in work with him and then independently, we reprove this. I reproved this with Lu. This condition holds that when you're in 1 dimension higher, then the same result holds, so that you have the similar sharpness when you're right below that of the cylinder. And again, the crucial kind of result that both of us proved kind of in different ways was that when your entropy is below that of the cylinder and you start connected, then any weak mean curvature flow stays connected. And that's sort of the crucial ingredient you need in Sheng Wen's argument to kind of make this sort of thing work. So I would expect a similar result holds in all dimensions, but we definitely can't prove that. So I think I'm out of time, so I'm going to stop here. So thank you for your attention.